All right, hi everyone. It's 11 o'clock, so we'll get, or sorry, it's 10 o'clock, so we'll get started. I can't wait till it's 11 o'clock. It's 10, so we'll get started. We're going to spend the next 45 minutes or so talking about deep learning, but in the context of feature and tabular data, so vector data, as well as some examples for time series. So my name is Nick Ginner. I'm a product manager at Esri, and I work in the spatial analysis and data science capability area. And I'm here with my colleague, Karthik.
Hi, my name is Karthik. I work as a data scientist in the GeoAI team.
And we're very excited to be here, and thank you all for being here. I know it's the last session, so stick with us, and let's wrap this thing up. So we have an agenda here. It's going to be pretty demonstration heavy for the next 45 minutes or so, but I do want to kind of paint the picture of what our GeoAI story is at Esri and how feature, tabular, and time series data fits into it. We'll talk about automated machine learning. We'll talk about understanding and explaining kind of what's going on behind the scenes of a machine learning or deep learning model. We'll talk about some techniques for working with time series data, and then we'll give you a couple of resources for you to get started and do some of this work on your own. So in general, I'm sure if you've been here a couple days this week, you've heard about AI and it's everywhere, and it's a hot topic item, even way outside of this Esri conference in the geospatial world. So AI is really about teaching computers, teaching machines how to do human tasks. Seeing and reading text data and performing analysis and learning patterns in data. And the whole sort of revolution in generative AI is actually creating new information, creating pictures, creating art, creating music, creating imagery, and so forth. And so we could apply these kind of concepts of letting a machine do work for the human, and we could apply those to geospatial problems. So the seeing is kind of the long history of photo interpretation of imagery in GIS and actually looking at satellite imagery and drawing polygons and drawing boxes around things and teasing out geographic information. So GeoAI could do that, being able to computer extract information from imagery and from LiDAR data. The middle section here, read, we can now let the machine read text data, understand text data, and tease out things like location and tease out other pieces of information, and even do things like take text descriptions of shapes and actually draw those shapes on the map. So this is a really powerful way to take documents and reports and actually create geospatial data from them. In the top right, analysis. And I think we're going to kind of hang out mostly in this section for today. But these are your traditional techniques of prediction and regression and classification and clustering that can be applied generally to vector data, which we've been able to do in GIS for many, many years. But when you kind of bring advanced machine learning algorithms and advanced deep learning algorithms, they provide new ways to solve these traditional geospatial problems. Of course, I mentioned learning patterns in data, and of course I mentioned creating new data. In this case, examples of taking coarse resolution imagery and actually creating finer resolution examples of that data. So we could apply these kind of concepts of letting the machine do the work of a human, which is AI, and we could apply those to geospatial scenarios and so forth. So the way that GeoAI is exposed within the ArcGIS system is at a couple of different levels, and you'll see at least two of these today. At the basis is the ArcGIS API for Python. This is a Python package that has many different modules for working with and interacting with your web GIS, for administering content, for administering groups and users, for doing spatial data science. But there's a specific module in the Python API called the arcgis.learn module, which is where all of the technology and all the development happens for our deep learning tools. So this is the sort of lowest level that we have within the technology. This is the developer experience. This is the code writing experience. In the past few years, we've actually taken a whole bunch of that functionality and wrapped it up into much more user interface driven ways to access these tools, specifically in ArcGIS Pro. So an entire toolbox dedicated to these GeoAI tools, but in a non-code different way. And then specifically for some of the imagery workflows and working with LiDAR and some of the text data, we've actually built a couple of dozen pre-trained models that do a lot of the hard work in terms of data collection and training of models to help you solve specific problems. Today, we're going to focus kind of in the first two, the Python API and the tools. These are the ways that you could access these types of tools within the system. And so again, today is all about the feature, tabular, and time series. We'll talk about automated machine learning. We'll talk about time series forecasting. As I mentioned, tools to do prediction, classification, clustering, and again, they're exposed through the arcgis.learn module of the Python API and the GeoAI toolbox. And so just kind of some of the topics that we've been working on. Again, you'll see AutoML. Karthik today will show you multimodal input for AutoML. So in addition to the actual the columns in the table, let's say you can make a prediction based on the columns in the table, but also an image attachment, as well as maybe a text description of something in that table. So it's multiple modes of data that are contributing to a prediction. Additionally, there's been some new work in terms of time series, so advancing time series to give you the ability to actually forecast multiple time steps in the future, and some advanced techniques for time series forecasting and prediction with deep learning and allowing you to address more complex patterns in your data. So I want to start off with just a few concepts here. There's a lot of terminology with deep learning, and you might be thinking to yourself, like, what even makes it deep? And I think it's kind of hard to conceptualize sometimes. So I'll take 5 minutes just to try to break down some of the concepts behind some of the algorithms that are used. And hopefully this at least gives you a little bit of an understanding of how these things could be different. So this little table right here, let's just say that this is an attribute table. And the goal here, let's say that we're looking at a data set of house locations, and we're trying to predict how much a house will cost. So it's like a home valuation type of study. So here's the price of each house in this data set. And what informs the price of a house? Well, how many bedrooms it has, how many bathrooms it has, square feet of living space, the number of floors, is it close to a waterfront, what condition, how old it is, etc. So if we all live in some sort of structure, and there's a number of characteristics of that structure which informs how much it costs, right? So we need to use all of this information to predict the price of the house. That's the kind of goal here. Now, the sort of most classic and basic way to do this is to do a linear regression. And that basically says, all right, the price of a house is informed by the number of bedrooms, the number of bathrooms, the square feet of living space, and a whole bunch of other variables. But each one of those is multiplied by a coefficient, slash a weight, slash a parameter, all the sort of same use of the term. So it's like I'm predicting the price of my house based on the number of bedrooms and bathrooms and square feet of living space and others. But in order to generalize that to the entire data set, each one of these has a little weight associated with it. And these weights, you can think of these as sort of like a knob that you turn. Like, turn this knob a little bit and multiply it by the bedrooms, and it kind of changes the price a little bit. I turn this knob a little bit and multiply it by the bathrooms, it kind of changes the price a little bit. So think about like when you wash your hands and you're kind of like playing with the hot and the cold, and you're just kind of tweaking those to get to the right temperature. That's what these weights do in an algorithm such as this. It's little tiny changes in numbers that affect the end prediction, which is in this case the price. So for a linear regression such as this, there are, I don't know, maybe 6 different weights that you're tweaking. Very simple. We move on to another type of algorithm, which is something called a decision tree. And this is a classic machine learning problem. But instead of this kind of weighted linear combination, what it does is it takes in all the data and it kind of builds this tree of little tiny binary splits. So think about it like if a house has more than 3 bedrooms and it's close to a waterfront and it has this much living space, then it might be worth this much money. But if it has less than 3 bedrooms and it has more than a certain amount of living space and it's not close to a waterfront, it might have this price. So it's kind of taking that same problem and it's breaking it down into a tree-like structure where at the bottom, you make a prediction of price. Little tiny binary decisions. That's why it's called a decision tree. Take that a step further, and you hear about algorithms like random forest, and you hear about algorithms like gradient boosting. What a random forest is it's a whole bunch of decision trees. Right? Lots of trees make up a forest. It's a whole bunch of decision trees that are all built with kind of tiny subsets of the rows and columns from the entire data set. So the idea of a random forest is that you're sort of building these little tiny trees that don't do that great at prediction, but when you build a whole bunch of them and you average all the predictions, they usually end up doing a really good job. So it's like a random forest is a bunch of decision trees with random variables. Take that a step further, XGBoost, it's a similar concept where it's essentially a forest full of little decision trees, but instead of doing these all little trees in parallel, it's like you make a prediction from one tree, and then based on how well that tree does, you let the performance of the first tree improve how the second tree is trained, and then you let the prediction in the third tree and the error in the third tree inform the next tree. So you're kind of building these sequential trees that learn from one another as they go. It's a machine learning. We take it one step further, and obviously the title of this talk is Deep Learning. Deep learning is really all about neural networks. And so a neural network is kind of this idea of little tiny simple methods that are chained together and eventually produce somewhat of an output or a prediction. So in this case, let's say we take our input data, and it's just one row of data about the price. And essentially what we're doing is we are inputting that row of data, and we're inputting it into these different layers of information. So take this little layer of information right here. Think about this as like one little linear regression right here that produces a number. And then another little linear regression that produces a number. And then all of these little linear regressions have all those different weights, as I mentioned. So a linear regression has just a couple of weights. This now has dozens, thousands, hundreds, millions, billions of weights a neural network could have. So the point is that as you get more complex, you have way many more knobs to turn. Okay? So when we think about large language models, but billions of parameters, right? Imagine you're making a prediction and there's billions of little tiny knobs to tweak that changes that data, that changes that prediction. So the point here of this slide is to kind of understand that there's multiple sort of levels of ways to make predictions in data with machine learning and deep learning. And they could be from very simple and easy to understand to very complex with a lot of different kind of things going on behind the scenes. And this hopefully paints the picture of some of that for you. So we'll go through some of these today. Now, as far as accessing this in ArcGIS, as I mentioned, you can use the arcgis.learn module. There's different classes for machine learning models. There are different classes to actually use a fully connected neural network for tabular data. And then there's also AutoML, and that's what we're going to focus on today. Having the ability to do machine learning in an automated way and letting the computer kind of do some of the manual time-consuming steps for you. And then we also have the ArcGIS Pro GeoAI Toolbox, which has 2 tools for training an AutoML model and then using that model to make predictions. So what's AutoML? Well, let's think about the process for doing a predictive type of problem. You got to decide what the problem is. I'm trying to predict the price of a house. You have to get your data. I need information about the number of bedrooms, the number of bathrooms, the square feet of living space, et cetera, et cetera. Then there's this kind of circular set of steps where you might need to clean and pre-process the data. You might need to engineer it and add new columns. You then get into the step of training a model. This notion of hyperparameter tuning, this kind of gets at what I was saying about tweaking knobs, right? There's a lot of knobs that need to be adjusted slightly and see how that impacts the price and see how that impacts the prediction. And this is also about turning the knobs for how the actual algorithms work. And then there's, let me look to see how I did. How well did this model perform? Can I interpret the results? Does it make sense? Now, what AutoML is made to do is to kind of take this middle section and kind of let the computer do some of that for you. Well, let me try a whole bunch of different models and see how they work. Let me try a whole bunch of different models and then also take some of these hyperparameters and change some of those and see how that impacts the results. So this section in the middle here is about, I don't have to sit here and run model 1, wait for it to run, look at the results, change some knobs, run it again. It's like, let the computer do this for me for like 2 hours. And then I'm going to go and see how all these things compare. Automated machine learning. And in the context of the tools that we're going to show you, this section here on model training, well, this actually, you have the ability to kind of loop through several different algorithms to see which algorithm is the most appropriate, perhaps, for your data and for your problem at hand. And so you see in here, I just talked about random forests, and I talked about decision trees and linear regression and gradient boosting. And so what I will show you is actually using AutoML and saying, here's my data, here's my problem, have a go at it, and then let's come back and look, and let's see if we need to tweak anything. So let's get into some demonstrations. So let me provide some context for what I'm going to show you here. So this is a map of Chicago in the US, and this map is showing the demand for rideshare pickups. So where the areas are more yellow, that's where there's more demand for Ubers and Lyfts and other types of rideshare type of pickups. So I have this data set, and these are census tracts in Chicago. What I also have, and actually let's take a look at some of the information I have here. So let's look at the attribute table. Okay, so what do I know about these census tracts? I have information for the number of, or sorry, the percent of the population with bachelor's degrees, sort of adult age 18 to 34, the population density, and I have a whole bunch of attributes on employment characteristics and how many commuters there are, and is it walkable, is it, what does the crime rate look like, et cetera. So I'm trying to understand the demand for rideshare based on employment characteristics and demographic characteristics and sort of characteristics of the urban environment. So think of those as like the columns that I'm using to predict. I also have here a map of crime density, and I have some information about where there are bus stops in Chicago, as well as where the train, where the L stops are in Chicago. So I have tabular data, and I also have point data, location, and I have some raster data. So in the GeoAI toolbox, as I mentioned, there are several tools for working with imagery and text and time series, and I'm going to just get into this feature in Tabular right here, and I can open up the train using AutoML tool. So this tool, input training features, I'm going to point to the data set for the rideshare in Chicago, which you're seeing right here on the map. There, we'll let for the tool load here. And I'll turn on my crime as well. This will create an output model for me, so it's a deep learning package that I could then use. So this deep learning package, it will know what drives rideshare demand in Chicago, and maybe then I could use that to predict what rideshare might look like in another city. My variable to predict, I'm going to be predicting let's see here, the trip count. Where's the trip count? Here we go, trip count. And here, under explanatory training variables, I'm going to choose several of those. Bachelor's, information about education levels, population density, age, job entropy, walkability, et cetera, et cetera. So I choose here my independent variables. Okay. Within this tool, I also have the ability to use explanatory training distance features. So think of this as, what am I measuring the distance from? Well, probably rideshare demand might be driven by how close you live to a metro stop and by how close you live to, say, a bus station. We'll choose in bus station. And then I'm also going to choose an explanatory training distance raster, and I'm going to choose crime density. So you see here, we're not only using the columns of the data, but we're actually using geospatial data to create other variables for us to help understand this process. There's a couple of different modes of AutoML. I'm going to choose basic. This is going to give me the most explainability, but as you get into intermediate and advanced, behind the scenes, there's more of the sort of hyperparameter tuning and more of trying different variables. So there's different levels that you could choose. You could set the amount of time you want the AutoML to run for. Here I could choose a particular algorithm, or I could just not choose anything and let the tool try them all. And I have some additional information about output reports and other options. So Karthik will talk more about the reports, but in the interest of time, let's say I ran this, and I ended up with a model. It's a deep learning package. What I could then do is I could open up the predict using AutoML tool, and I could call that model that I've trained on the Chicago data, and I'm creating predictions. And here, under input prediction features, I would take data from Atlanta, where I have all that attribute information and crime and bus stops and metro stops. And the same for New York City, where I have all that information, or Los Angeles. So I'm taking a data set, a model that I trained on a data set for Chicago, and I'm applying that trained model to several other cities where I have all that same data, all that same tabular data and information, again, about the bus stops, and in New York City, the subways and the crime, et cetera. So this predict using AutoML tool applies a trained model to a data set that has similar characteristics. So in the interest of time, again, let's say we took the trained model in Chicago, and if we go to Atlanta, we could see here that the predictions of rideshare demand can be made for Atlanta, they can be made for New York City, they can be made for Los Angeles, Philadelphia, et cetera, et cetera. So that's an example of using AutoML and kind of how to use the tool in ArcGIS Pro to train a model using tabular data, explanatory rasters, and distance features, and then apply that trained model, the deep learning package, to, in this case, other cities to make a prediction about the same type of problem. So I'll pass it to you, Karthik. And you are number
4.
Number 4.
3.
And we have to do a quick mouse share here, too. Mm-hmm.
So what Nick showed was how we could use AutoML from within the ArcGIS Pro. So there's another way of doing the same thing by using the API. So I just want to first understand if anybody in the room has already used the Python API, the ArcGIS API for Python. Okay, and specifically the learn module, if you have used the learn module before. Okay, very few. So the ArcGIS API for Python has the support for training the machine learning models and the deep learning models within the learn module here. So within the learn module, we have support for tabular data, we have support for 3D data, we have support for imagery, and we have support for text. So we have support for all of these different data types, and we have various algorithms that can train the models on each of these data types. So specifically, when we look at the tabular and feature data, we have ML model class, we have fully connected network, we have time series models, and yeah. So each of these you can go through these, and so these are the API signatures. So there are various methods available in each of these classes, and you can use them to train your own data from within the notebook environment. So let's concentrate more on the AutoML part. I use AutoML. Earlier, probably a couple of years back, I used to use ML model class, fully connected networks. But there are certain challenges which Nick spoke about. There is this whole process of iteration that we'll have to do, create your training data and evaluate your training data, and then evaluate your data across multiple algorithms. So there are various algorithms. There's a random forest model, there's an XGBoost model. You never know which works best for your data. So we'll have to train a model on all of these data sets, on all of these models, and then evaluate them, do some feature engineering. So all of that takes time. There are various hyperparameters associated with each of these as well. So it's not a simple task, and even if it is simple for some of us, but it is still time consuming. So AutoML solves all of those issues which we face. So I'm mostly going to concentrate on the AutoML part, and let's see how we can do that and within the notebook. So this is how we import the AutoML class. We have the arcgis.learn module, and we import the prepare tabular data, which helps me to prepare my data. I might have my data within a feature class. I might have it in a feature layer, rasters. I bring all of those together and create a data frame. So the data frame is the object which I'm going to use within the notebook, and using which I'm going to combine all of the different data types and from the different data sources, combine them all into a data frame. So I import the prepare tabular data, and I also import the AutoML class. So I get my data from, you can source your data from feature classes. Let's say I have my data in the feature class like this. So this data set is an Airbnb data set. It has some columns related to who the host is, some of the characteristics of the host, and what property type it is, and how many people it can accommodate, how many beds are there, and what's the price, and the number of reviews. And we also have a text column where we have a description of where the property is, the neighborhood of the property. So Nick mentioned a little bit about how we can combine the tabular data with the text columns if we have any, and if we have any images as well. So I'll be also touching upon those aspects. So if we have the data in a feature class like this, we can bring it to our notebooks and to a data frame by calling this method, and I pass the source of my feature class, and I get all my data within a data frame. My data frame or my feature class might have hundreds of variables. I might not want to use all of them. I probably want to use, let's say, 10 or 15 of those, and I can instantiate which variables I want to use within this list here, and I can also specify if some of those are categorical variables. So I can specify, I can name the variable here and follow that with a true or false. If I say true, it means it's a categorical variable, and if I says false, it's a continuous variable. So I declare all my variables and what variable types they are, and then I proceed towards preparing my data. So preparing the data is to pass your data frame, and then we also specify which is the variable within my data frame which I want to predict. In this case, I want to predict the price, and I also specify what are my explanatory variables are. So my explanatory variables are my independent variables, the variables which will help me to build my model. So I can specify that here, and then I call the prepare tabular data method. So when I do that, I get a much more refined data frame, which looks something like this. What is happening here is the text column which I had. So I had a text column, if you remember. So the text column was the neighborhood overview column. So all of those text has been converted into embeddings. So machine learning models cannot use text as it is. We'll have to convert it into some form of number. So what the prepare tabular data method has done for us is to convert those text columns into embeddings. So these embeddings are, you can term it as just a numerical representation of each of these text. So we get close to about 700, more than 750 columns for each of my text column that I have. So it essentially breaks down my text column into these numbered columns. I can use this numbered columns, combine them with my other tabular data, and then now build a machine learning model on top of it. So this is how we have also used the image as well. So if you have an image, I can specify where my image is, and what the prepare tabular data method does is to convert those images as well into embeddings. So if you have images and text, so I'll have close to about 760 columns for the representation of the text, and I'll have, let's say, additional 512 columns for the representation of my image. So I can combine all of those with my other tabular data and then train the model. So there are some utility methods like the show batch here. So show batch allows you to visualize your data, get a glimpse of what your data looks like. So you get the data object by calling the prepare tabular data method, and then I can call some of these methods like the show batch to see how well or how the data actually looks like. So once I have that, I'll instantiate my AutoML class by passing the data object. So it also has some other parameters. So it has different modes. It can take in the different algorithms. It can take in the different metrics. Some of those things, the same things which you saw in the UI, or in the geoprocessing tool, which Nick showed. So all of those things can be done from within the notebook here. So there are 3 modes. So Nick mentioned that we have the basic mode, intermediate mode, and the advanced mode. I would like to spend probably a minute more to explain what these modes are. In the basic mode, we just take the data as it is, and we pass it through variety of models. So we have, let's say, a random forest model, XGBoost, CatBoost, and LightGBM. So we just pass the data to all of these models, and with default parameters. We don't do any hyperparameter tuning here. We don't do any feature engineering here. We don't do any feature selection. Just take the data, pass it to all of these models, figure out what works best for our data. So this is the basic mode, and it also helps us to understand what are the most important features in our data set, which features influences my model the most. So all of those can be done using the basic mode. So the next is the advanced mode. In the advanced mode, you have more control over getting a better model. So let's say if you want to do hyperparameter tuning, each of these models, random forest has more than 10 hyperparameters which you can tweak. And there's a LightGBM model which has, again, more than 25 parameters which you can tweak. There's an XGBoost model, again, more than 25 parameters which you can tweak. So all of these hyperparameter tuning is done in the advanced mode. It is not done in the basic mode. And there's also a concept of feature engineering. Feature engineering is where you combine the data present in your features like this. So for example, let's say I have the column for beds, and I have a column for the bathrooms. So I can combine these and create a new feature. It might not look very intuitive for humans, but when the machines do this, we always end up getting better variables, which will help us to train better models. So that process is called feature engineering. And there is also feature selection. So even though we have, let's say, in my data set, I have close to about 780 different columns. So I probably would not need all of these 780 columns. So I'll probably need, let's say, 400 or 500. So the feature selection is also an important part. So feature selection is also done in the advanced mode. So advanced mode is more for if you want to get the most juice out of your machine learning models, if you want to get the highest performance. So that's when you can use the advanced mode. But then it also takes a lot of time to train these models. So the AutoML, what it does is it creates a lot of combination of all of your models, and it will try out all of these combinations. So it will take a lot of time to arrive at the best model. And then we can also specify the metric. If the default metric for, let's say, a classification model is a log loss, but if you want to use some other metric to do the evaluation, you could specify that. And you could also specify the sensitive variables. So this is a new feature which we have added recently to the AutoML. So if there have been some concerns in the past that the machine learning models usually amplify the biases which we have in the data set. So if there's a bias in your data set which is biased towards a particular aspect of your, let's say, or particular let's say there's a minority class and you don't want the model to be influenced by that minority class, or if you don't want your model to be influenced by the majority class. So there are ways in which you could train the model by also considering these fairness aspects. So we have a whole lot of fairness features which we have implemented recently. I won't be going too deep into the fairness aspect today, but all of those details are present inside the page here. So once I create the model object, I can call the fit method. It will, you can see that it is trying out the different models, and it is checking which of, and has an evaluation metric for each of those. And finally, it tries out a bunch of models and it figures out which one works best. One aspect which I would like to talk about here is an ensemble. So at the end, after trying all of these models, what the AutoML tool also does is to combine the outputs of different models. We have an, let's say, a LightGBM model, we have an XGBoost model. So usually, combining different models and getting the average of those two or three different models and getting that average is what actually works best. This ensemble is a process or a way in which we can combine the output of each of these different models and get a better output. So that's an ensemble model. So, and finally, we can also generate a report. Once we have the model trained, we can also generate a report. And the report looks something like this. So it will say which were the different models that were tried out, what combinations were tried out, and which one was the best, and also the associated metric value for each of those. Let me also show the report in slightly more detail now. So what the report shows here is, as it said, it's a leaderboard of how your models performed, and some charts which will help you to visualize that, and the coefficients of Spearman correlations of the models, so how well each of these models are correlated with each other. So you can see that in this report. And if you click on any one of these, so it will also give you some insights on what were the hyperparameters that were used to train this model. So in this case, the extra trees was a model that was used, and these here shows what were the hyperparameters that were used in order to train this model. And some of the additional metrics, if you are interested to know not just the RMSE, but if you want to know also, let's say, the MAE or the R-squared values for the model, so you can get this information from this page. It will also show an importance. So the importance, the sharp importance, it will give you a sharp importance. It is basically telling which aspects of my data or which columns in my data set had the most impact on building this model. So in this particular example, I can see that this particular column had the biggest impact on training my model. So this feature will help the person who is building the model to understand a little bit of what is going on and why is a model giving a prediction which it is giving. So this is one way of getting that. There's also another way which I'll now touch upon. So once you create the model, you save that model, and then I can use this model to do the prediction on a new data set. So I can call the predict method. So this is similar to the predict using AutoML tool, which Nick showed. So you can use the predict, you can save the model. Once you get the model, you can call that predict on a completely new data set, as long as it has the same variables within the data set as well. So yeah, the next thing which I want to talk about is the predict using AutoML tool. So one aspect which I would like to show here is getting the explanation for each prediction. This is one feature which has been requested by the users in the past. So let's say I apply for a loan for a bank, and now the bank has an automated way of granting the loan or processing my loan information. So now they use a machine learning model, and the machine learning model looks at all my data, and then it says that, no, I cannot give the loan to you. But I, as a customer, would be interested to understand why the loan was not granted to me. And so what this particular feature does is to explain why a decision was taken. If the decision was, let's say, no for a specific problem, then it will help us to understand why the model said no. So if you're interested to get such explanation, you can click on this checkbox here when you run the predict tool, and you can get the explanation. And the explanation looks something like this. So here, for this particular example, you can see that the property type had the most impact on deciding whether the price of the property should be, let's say, 50 or 60 or whatever. So, and it could be different for a different example. So for example, let me take a different example here. So here the neighborhood is the most important feature. So in my case, let's come back to the example of loan application. So I apply for a loan. In my case, it is possible that, let's say, my salary is not enough. That's the reason why the bank says no. And for a different customer, it could be some other reason. So each of these prediction has its own reason. And this chart here will help us to understand why a specific decision was taken for each of the prediction that was made by the model. So this is a new feature of the model explainability that we have added recently, and this has been a popular request in the past, and I hope some of you here would find it useful. So this was about AutoML. So now what I would like to do is to talk a little bit more about the time series. So in time series, yeah, I have again a notebook where I would like to show an example of how we can use time series. But if you have a data set where you have data from the last 5 years, and you have let's say a value for each time step, and if you want to create or forecast the value for the next 10 steps, so that's an example of time series use case. So in this notebook, what we are trying to do is to forecast the power consumption for a city of Tetuan. It's a city in Morocco. So we have the data from 2017. We have the power consumption for every 10 minutes for that city. And what we would like to do is to forecast the power consumption for this city for the next, let's say, 2 days. So you can imagine the kind of application that such a use case could help a utility company. So to do that, we can again use the time series model in the arcgis.learn API. So I have my data within a layer here on ArcGIS Online. I get the data, I take the data from this particular item, get the data and load it into a data frame. So the data looks something like this. I have, starting from 2017, the 1st of January, 12 a.m. So I have the power consumption for the city, and I also have certain other variables for that city. I have the temperature, the humidity, wind speed, and all of these. So all of these influence the power consumption of a city. So now I can use this data for the last 5 years, and I can forecast what would be the power consumption of the city for the next 2 or 3 days. So to do that, there are different approaches available within the arcgis.learn API. The first approach is to use a univariate forecasting. Univariate forecasting is where I just use the power consumption for the last 5 years and use that data to forecast for the next, let's say, 2 days. in the univariate forecasting, I'm not going to make use of any of these other variables which I have. I'm just going to make use of the total power consumption, and I'm going to use this column to forecast the next, let's say, 2 days power consumption. So to do that, I first split my data using the train test split method. I pass in the data frame, and I say how much of my data is to be saved for later use. Let's say I call it as a test size, and then pass that information, and then I create a train and a test data set. I'm going to use only the trains data set for my model training, and I'm going to keep aside the test data set. So, and then I can also do some visualization using the autocorrelation plots. The autocorrelation plots helps us to understand if my data is actually fit to be used for a time series. If my data is not fit for a time series use case, I'll not be able to train a good model using the time series model. So this graph here, this curve shows the autocorrelation of my data, and as I increase the lag from 0 to 50,000, I can see that the size of this chart keeps getting smaller. So this indicates that my data is an actual fit for a time series use case. So once I have that, I call the prepare tabular data method, similar to what I used in the AutoML. I call the prepare tabular data method. I specify, I pass in my data frame, and I specify which is a column I want to predict, and then I also pass in the time step. In this case, that my time step is in the date time column. And I can also visualize my data by calling the show batch. The same thing which we did with the AutoML, we have the similar method here as well. And then instantiate the model. So there are various model architectures available. We have LSTM, we have time series transformers, we have inception times. You could use any of those model architecture to train your own time series model. So this is a deep learning model. So what we are going to use here is a deep learning model. LSTM is a deep learning architecture. So I need to, it's a neural network. I'll need to find out what my learning rate is, and we have a method for that. And once I have the learning rate, I can use that and call the fit method here. So this is my time series model object, and I call the fit method. I can specify the number of epochs I want to train my model for, and then run get the model. So once the model is trained, I can visualize the results by calling the show results method. And then finally, I can also, there are methods which will allow me to calculate how the model is performing, figure out how well the model is performing, and then also call the predict method. So we also have a predict method. So if you remember, I had kept aside some portion of my data aside for testing, and now I'm going to call the predict method on my test data. So and then finally, I can see how well the model is performing by calculating the R² value here. So this was univariate forecasting, where I just used only the column or the forecast variable in order to do the forecast for the next couple of days. I can also I can train much better models. This is a new feature that has been recently added, where I also use the other aspects of my data. For example, the humidity, the temperature, all of those variables will help me to get a better model. So to do that, I again create the training data, and then I split my data again. This time the only difference is earlier I was just using this column, and now I'm going to use these columns as well to get the forecast. So this is called as multivariate training. Earlier what I did was univariate forecasting, and what I'm going to do is multivariate forecasting. The only difference between the steps which I took in the previous while I did the univariate forecasting and what I'm going to do now is I'm also going to pass the explanatory variables. If you remember, or if you had noticed, I just passed the train variable previously and just passed the predictor variable. I didn't pass the explanatory variable. This time I'm also going to pass the explanatory variables. So when I do that, the model, I can also then specify the model here. This time I'm going to use an inception time model and then do the training. So the same thing which I did in the, with the univariate, I'm going to do this training the same way, and I can train a multivariate model now. So usually what we have seen in the past is we have tried this approach of univariate and multivariate across different data sets. And it's always the multivariate data that usually works well for us. So I hope this, again, this new feature which we have added will be useful. And again, once I have the model, save the model, and I can call this model, I can call the predict method on my new data set to get the forecast. So that was about time series. So I think we are close to, yeah. Okay, so the last aspect which I would like to show you is some of the resources that we have available for the time series and the tabular data. So we have the developers page for Python API, and within that we have several samples. And within the samples, we have samples for computer vision, we have samples for NLP, we have samples for tabular data. And within the tabular data, you can see some samples. These are the samples which you can run as it is. You have the data available here. You have the notebook available. You can take it to your own environments and run them to get the same results. This will help the new users to understand how to use the API on your own data sets. So that is all I had for today. So Nick, do you want to add something, or can we take questions?
Sure, I think we could probably switch back here. Yeah, and just one note on the sample notebooks that Karthik is showing there. You know, not only is it a great way to grab the code and repeat this so you kind of learn the process, but what I do is basically take all the code and I just pull out the feature layer that's provided here and I put in my data, and then that's a great way to apply the steps and the workflow to your data, and it's a great way to learn this, and it's a great way to not be intimidated by writing code, right? So you just kind of input what's here and change it to your data, tweak some things, and that's how you learn how to use these. So they're super, super valuable and popular. And then I guess with that, if you wouldn't mind, we take the feedback very seriously. So we hope that you enjoyed this and that you have, well, I guess I would say a great remainder of the conference, but I think this is pretty much it. I guess there's just the closing section next. So hopefully it was a great week, and hopefully this is helpful. Let us know if you have any questions, and safe travels home. Thanks. Yeah, we'll take some questions. Go ahead.
Thank you for your presentation.
Sure.
I'm very new for the machine learning. I need to change the text to number. The text is not accepted for the machine learning, right?
You want to take the mic?
Thank you for your presentation.
Sure.
I'm very new for the machine learning. So you said the text is not acceptable for the machine learning, right? So how do you convert to the text to numbers?
So what we do is take the text column and pass it through a neural network. We have a pre-trained neural network and with a BERT architecture. So we pass the data through the BERT architecture and get the embeddings. So when you pass the text column, text data through these kind of neural network architecture, so the text gets broken down into numbers. It's again a neural network architecture, and it will give us a list of numbers. So let's say 768 numbers. And it depends. The number of embeddings that gets extracted depends on model to model. So if I use a BERT model, I get 768 embeddings. If I use a different architecture, so I'll get a different set of embeddings. Each of these different architecture will have a different way of representing your text data. So it makes it as accurate as possible to represent your text data in a tabular or in terms of numbers. That's how we do that.
So the concept is embeddings.
Embeddings, yes.
And maybe a more simple way to think about this is if you, let's say that you had just a column in your data that was yes or no. Yes or no. To use that in a neural network, you need to make it 0 and 1. So it's, what he's saying is that you're taking text and turning it into numbers. There's obviously much more to it than that, but that's, I think, the general gist of it, through a concept called embeddings.
In AutoML, you use the fixed set of explanatory variables with different models and test it with different models. So is it doable to use different sets of explanatory variables tested with different models?
If I were doing it manually, I would have done that. But now that's the power of AutoML. We don't have to do that. What we have to do is just pass in all of your data. If you have 100 columns, just pass in all of these 100 columns and let AutoML figure out which of these 100 columns are important and which of them are not. So what AutoML does is it will do a feature selection. When I say feature selection, it takes in these 100 columns and figures out which of these 100 are important for me. It will only take those important ones and use those for building the model. So I don't have to do it myself. It is automated within the AutoML tool itself.
And does that sorry, just to add on to that, does that differ by the mode though?
Yes. So you can do that feature selection only in the advanced mode. So there are 3 modes, basic mode, advanced mode, and the intermediate mode. So within the advanced mode, you can do all of these feature selection and feature engineering. It's not available in the basic mode.
I just wanted to make sure. So my understanding, you run these things from Pro, you're actually making your machine do the work, right? And then when you run it from ArcGIS API for Python, it still is your machine doing the work, right? Okay.
Yes. Yep. It's just a code way to do it versus a tool way to do it.
So for using the ArcGIS Python API and doing the AutoML, you said it creates a model definition, right? So then can I take that model definition and give it to a coworker and he can also use it?
So you can push your model online and as an item, you can download that item later and you could use it on a different machine altogether.
So long as your coworker has the data to, if you were giving them that model that they were then going to use a prediction on, they would have to make sure that the data that yes. The assumption I think would be that like I trained the model, gave it to Karthik, and he's using it to do prediction. So he would have to have the data to do the prediction on, but.
So the columns are the same. The attributes should be the same. The data, of course, would be different. So in the example which he showed, he trained the data on the Chicago data set, but he got the predictions for Atlanta, for New York.
So is there a way to consume these models in a web apps?
Right now, we do not. So for tabular and time series data within web apps, we do not, right?
I guess like if you made a geoprocessing service out of one of the tools, like you would have to take the steps to create that service, but in that case, these are geoprocessing tools, so they would, I assume, work like any other geoprocessing service that you create.
Hi, I like the idea with the AutoML is solving a lot of problems. Still, you will get many training sessions. Do you have a best practice how to run this training on a virtual machine? What do you need? Do you need ArcGIS installation and licenses?
You want to take that?
So if it's a virtual machine, well, we showed you the Python API. That Well, let's start with the Pro case. We showed you Pro Tools, so I would assume ArcGIS Pro would have to be installed in the virtual machine, and to use the GeoAI toolbox, you need to have an advanced license. And you also need, there's something called the deep learning installers. That's a whole set of Python packages that enable the deep learning side of things. So all of that could be put on a virtual machine. For the Python API, it would just be you would need the Python package and you'd need the deep learning installers. You wouldn't necessarily need Pro.
Yeah, you don't.
Yeah.
And if you're interested to know what are some of the best practices, we do have a page specific to the AutoML, where we talk about how to use the tool, how best to get the most of that out of the tool. So what are some of the best practices which we can use? So if probably he'll bring up the page now.
Just the Pro doc?
The Pro doc, yeah. Yeah. So the first one.
Oh, sorry. Yep.
So this page here, here we talk more about how to use the tool, how to use the different parameters, and what are some of the best practices while we do the training.
It's conceptual.